Good morning, everyone, and thank you for joining us for the second webinar from the RS4C project with the title Remote Sensing for the Non-Remote Sensing Practitioners. And this is part 2 as a continuation of the first webinar we had on October 16th. And today we will dive a bit deeper into the application and use of remote sensing for water and environmental applications. Alga will take over to introduce the speakers for today.
So today we have two speakers. We have Dr. Sajid Parit from Expo City Dubai, and one colleague, Dr. Belfrid Dijowesi, my apologies for the pronunciation, from UAC Benin. I would like to ask Dr. Sajid perhaps to start with his presentation on the topic development, remote sensing for monitoring and quantify water resources.
Hey, thank you, Elga, and I hope you all can hear me very well.
Yes, we can. I mean, I can.
Okay, great. So I'm Sajid Parit. I work mainly on water management domain using technologies like Earth observation, IoTs, and other digital interventions happening. I have around 15 years of experience in this field. I was working with the IMI before and IHE Delft. So Elga, Claire, and Amani, Solomon, they were my colleagues before. And recently I moved to an institute in Dubai. So I'm joining you from Dubai now. And today I will give you an overview of what can we do with remote sensing in monitoring water, freshwater resources. Let me share my screen before I go on with my speech. Okay, I'm sharing the entire screen. I hope you can all see it. Okay. Yeah, so before getting into the technical stuff, I just want to introduce where I am right now and the center which I'm working on. So as I said, my background is mainly remote sensing for water, agriculture, water management, and we work here in a center very close to the ministry in UAE, where we work mainly with climate resilience. And many of you know the context of why there is a lot of focus right now on climate resilience, especially in Middle East and North Africa and the South Asia, MEASA region, we call it. Especially with the unprecedented events from the rainfall and also on the water scarcity. We are also forced to work on climate resilience, especially from a built-in environment and also from a food security perspective as well. So our organization work mainly on these aspects. Especially there is a lot of focus on these topics after the recent big rainfall event which caused widespread disruption in Dubai and elsewhere in Middle East. So this is just to give you a context on where and why we work on what we work on. A couple of slides on our institute. So our institute is called Terra Center for Sustainability. We are not aiming at reinventing the wheel, but rather we are trying to connect the dots using data and the technology to derive actionable information to inform towards a resilient community, be it in a city, be it in a village, be it farmers. So we address community as a whole, and we have many programs addressing communities, grassroots level programs addressing communities, and also we have a huge school education program where we try to integrate sustainability and related topics in the school curriculums. So this in overall what we work on in our agency, with the three pillars where we develop, we communicate, and also educate. So we have a center with renewable energy, completely net zero building, and um, implementing and developing programs on several aspects of sustainability and biodiversity. So that was a bit on the background where I am, the center where I'm sitting here with the ministry, and coming back to the topic today. Just want to give you to start with um, why we are talking about water resources and what is the role of remote sensing on monitoring water resources. So this diagram gives you an overview of the freshwater sources actually, the lakes, the wetlands, how these are placed in the larger hydrological aspect, and how we can use either have the field-based monitoring, field-based measurements, or we can use technologies like satellites to monitor these sources. Now, why we are worried? Because the share of fresh water in the world, um, it's again the 2.5% of the world's available water is only 2.5% is fresh water, rest is saline or the seawater. And from this 2.5%, you might also know that the major share of the fresh water is used for irrigation. So there is limited water resources available. So it's very important to protect the resources for growing population and increasing food demand. The increasing demand for this already limited water resources is adding pressure on this. So it's very important to monitor the quality and the quantity of these water resources. Um, Added to that, the climate change impacts like increasing events of rainfall, increasing events of water scarcity and drought is also adding to the complexity of already complex situation. Um, I just added these two slides, but I also understand there was another webinar which covered the basics of remote sensing. But anyway, I'll just quickly go through it. Um, Remote sensing is the science of obtaining and interpreting information from a distance. So it can be any sensors which are not in physical contact with the object being observed. And the most popular one is the satellites from the space. So we have many satellites in space, thousands of them from different agencies, different government agencies, different private companies now monitoring Earth or taking snapshots or taking photographs, taking images of the Earth frequently, daily, weekly, bi-weekly, monthly, etc. So remote sensing, when we generally talk about remote sensing, it's about how to use this data from satellite to interpret what is happening on Earth, and we also call it Earth observation. It offers the remote sensing offers state of the system at a particular point in time and in two-dimensional space, so X and Y, and this also tell us how that particular system, for example, if there's a lake, how that lake is or the status of that lake over different time period. So that is another advantage of having frequent data coming from satellites. Sorry for the jargons, but there is an increasing popularity of remote sensing, especially using Earth observation satellites. So everyone is talking about it. So one reason is the lack of data coming from the field. It's also expensive to collect data from the field, and the coverage it can obtain is limited. So that is why there is a lot of traction on remote sensing using satellites. And there is an increasing trend over the years in getting images, high resolution images, and also getting very highly frequent images. For example, daily or every 2 days, we can get images from the satellite for the same area. So that means if we get a weekly image, we are talking about 12 months into 48 observations for your study area in a year. So that is the advantage, and we can also increase that into daily. Of course, it's not as magical as I say. There are a lot of challenges. One of the main challenge is the cloud cover, depending on the geographical area you are studying. So that is something which we need to always consider. So when we talk about daily data or weekly data, there will be a lot of days which we cannot use satellite data due to bad data quality because of cloud cover. Um, Potential of remote sensing is why we there is a wide there is an increasing demand for remote sensing, or even from a donor's perspective. If you look into international financial institutes who is investing heavily on infrastructure projects in irrigation, agriculture, etc., they are also interested quite a lot in remote sensing, because these data sets are very useful in doing impact assessment using historical data, because many times we have data available for last minimum 10 years to 20-25 years it is available. But in principle, we can also get data from 1980s. So there is historical data available. It will help us in assessing the state of the system, impact of different practices, impact of different policy interventions, different policies. For example, a biodiversity policy which came into picture in India in the 1980s, we can actually check using satellite data whether that has helped in improving the biodiversity in national parks and wildlife reserves. So that is one example of checking the impact of different policies using historical data. Um, to monitor the system, it can be an irrigation system, it can be a water source, it can be a lake, it can be an irrigation system. Near real time is possible, and it can also take a stock of extent of land and water use. It will also help us in planning future interventions in terms of, for example, financial investments. Um, Prediction is something which is gaining a lot of traction. So using this historical data and the near real-time data, how can we use that data to predict what will happen in the near future? What will be the state of a particular source or a particular biome? Um, yeah, in the near future. For example, in agricultural area, what will be the biomass or a yield by end of the season? So it will help us in ensuring potential outputs, planning intervention, and preparedness. So overall, I would say there is an increasing trend towards using maps to derive information and actionable outputs. So just making maps and stopping it there um, is not advised anymore. But there is a lot of push towards, okay, we have the maps, now what should we do? And what can we do? What are the recommendations? And where are the hotspots? Where are the bright spots? How much should we invest? So those kinds of questions, tangible answers, people have started seeking from remote sensing. Um, so why do we observe from space? Of course, due to the global and synoptic coverage, the satellites can coverage the entire globe in a day sometimes. But if it is higher resolution from a spatial point of view, then it's daily is not really feasible, but weekly, for example. Um, Now, in the case of water resources, we can also have a temporal frequency needed to capture dynamic aquatic process. And many times observations of remote locations where field-based reach is difficult is quite easy with the satellite data. Um, Now, when we talk about water, I mean, there are two aspects to it: measuring water availability and consumption. I'm not sure, maybe many of you are very familiar with this aspect. So that is mainly evapotranspiration which represents the consumptive water use and or water evapotranspired. In case of crops, we relate that to, or we call it a proxy for consumptive water use, and the precipitation, which represents the rainfall, which is the water coming into this system. So these two parameters, which forms the very basic or very important, two important variables in a water balance, um, can be measured using remote sensing. But in this talk, I don't want to focus on this because you must be hearing about this, the WAPR data set, the agriculture water management aspect, quite a lot in the project or in the previous webinar. So I want to focus more on optical properties of water from satellite data. So that represents the water quality. How can we, or what can we measure from satellites on water quality variables? For example, here we list some of the variables like chlorophyll, the clear water, and the organic matter, and the sediments. And there are other related variables like Secchi depth um, and other chemical variables which we can measure using satellite data. Not only measure, there are actually ready to use data sets available from satellite. So the rest of the talk, I want to focus on some practical data sets which are available on these aspects and the use cases, which would be useful for you to take up and use in your work. Um, so in terms of water, there are several satellites observe water surface properties in the open ocean, in inland lakes and coastal ocean and estuaries. So please keep in mind that when I talk about water surface, we are talking about surface water only here. So a number of water quality like temperature, which is very important, chlorophyll A, turbidity, CDOM, etc. We are also using satellite data to detect harmful algal bloom, especially in the marine ecosystems. And again, the near real-time data is available from many sources. For example, this image represents the chlorophyll A measured as in milligram per meter cube as of 1st June 2022. So this is the image representing that in real quantity. Another aspect to it is monitoring lakes and reservoirs using remote sensing data. So other than the biological variables or the physical variables like temperature, remote sensing can also measure the seasonal lake extents and water levels. As you see here, I'm using something called altimetry data. And the lake extents can be measured. The dynamics of lake extents can be measured using optical data sets coming from multiple satellites. Okay, so I will quickly move to another presentation here, which I want to focus a bit more on the practical data sets available. So why is it important, or why is it more close to users? Because there is an increasing availability of open data on water resources. So with availability of satellite data from 1980s, there are numerous data products available. The Sustainable Development Goals push further development of country-wide statistics, especially on water resources. And these statistics for the SDGs were mainly based on remote sensing because many of these countries don't have an inherent system for monitoring from the field. Both global and national products available. Most of the satellite data from NASA, the American Space Agency, and European Space Agency are open access. So that also triggered the development and widespread adoption of these data sets. Um, so next few slides, I will take you through some of the data sets, useful data sets and useful platforms related to monitoring water-related ecosystems or water sources. SDG 6.6, I mean, this is a very interesting application. The link is here. I will share these slides with the organizers. So this indicator tracks changes in different types of water-related ecosystems, enabling decision makers to determine the extent of a system or change over time. The advantage of this system is it's global, and the website or the web application gives can also give country-wide statistics on water resources um, through an interactive platform. So this is how it looks like. For example, I use this app to create a quick water resource statistics on water resources for the country of Uzbekistan. It also gives you a map of where the surface water areas are, and it gives you dynamics of permanent water, seasonal water. For the lakes, you can also get some of the biological aspects like turbidity states on water quality, the area of wetlands, mangroves, reservoirs, and lakes. So it is categorized very well. It gives you statistics on different water sources. And it's all based on remote sensing or satellite data.
Sajid, I'm sorry to interrupt. You have about maybe 3-4 minutes still.
Oh, okay. Sorry. Yeah. Okay. I'll be quick. So this is again for another country, Kazakhstan. There's another interesting resource is hydro lakes, where you can get the shoreline polygons of global lakes, not necessarily directly derived from remote sensing, but still it is the digital elevation model is one of the main source. We can still say that it's a remote sensing derived, but for any boundaries, this is quite useful. The Global Surface Water Dynamics, which is hosted by Joint Research Center in Italy. So it gives surface water dynamics from space at 30-meter resolution. Currently available from 1984 to 2019. I doubt. I think they have also updated it to 2021 or 22. I'm not sure. And yeah, if you go to this website, you can directly access it for any place for your countries. You can get all this data. Another important one is NASA Worldview. So it's also again an interactive web-based tool for browsing satellite imagery, and it also gives some of the water quality parameters such as chlorophyll A. As you see here, you can directly access it. I think if you check it today, you can also get the data for yesterday, for example. So it's very near real time. And you can download and you can do further analysis in tools like QGIS. Another one for water quality is Ocean Color. That is Copernicus Global Land Surface, where it offers globally lake water quality parameters called chlorophyll, trophic state index, and turbidity from 100 to 300 meter spatial resolution. It also gives data on lake surface water temperature, which is quite interesting for studies involving climate change, the warming of the lakes, and how it is related to the biota in the lakes. So those kind of studies, lake surface water temperature, is quite useful. The historical one. This is very interesting data set called Dahiti database. This gives you the water level of lakes and reservoirs. It is coming from the satellite altimeters. Around 6,813 water bodies are covered. I haven't checked it yet today. So currently it should be more, but it's derived from satellite altimeters. Yeah, for the capacity development, I mean, there are many training resources available, but I would really like to give a shout for NASA's Applied Remote Sensing Training Program, where you will find a lot of open training programs on using satellite observations for water quality and water resource monitoring. Water quality assessment that is coming directly from IHE Delft. I hope this is still ongoing. And there is another one coming from the Water Quality Standards Academy, which talks more about water quality standards and monitoring protocols. I will stop here. I think it will, if you have any questions now or later, I'll be happy to take it.
Thank you. Thank you, Sajid. Oh, there, Elga, go ahead. I thought you were muted.
Yeah, I was trying to unmute. Thank you very much, Sajid, for the nice overview and focusing on water quality component. Maybe we can take a couple of questions and then we move to the next speaker, if any questions. You can either raise your hand or we are a small group, so you can also just unmute and ask your question. Yes, I see one hand.
Nirmala.
And Nirmala, I think, was the first.
Hi. Hi, Elga. Thank you.
Hello.
Hey, hi.
Hi, Sajid. I have one question with regards to saltwater intrusion. Is it possible to use any of these remote sensing databases to figure out, say, for example, on the west coast of India, where the Western Ghats are, much of the rivers are harnessed, and the flow of the quantum of the flow of water into the ocean has reduced drastically over the last few decades. So there is saltwater intrusion into the estuaries and upstream of the lake,
Yeah.
rivers itself. So I was just wondering if there's any data set, or is there any way for us to determine how far inland has the salt water come in?
Um, Good question. There's no direct observation of salinity, for example, from remote sensing, but there are, of course, other characteristics of other chemical or biological characteristics of the water which can be used as a proxy for salinity. So there's no direct measurement to answer your question in a very short way.
Which water quality parameter can be used as a proxy?
We usually use for salinity. I need to check, but the Secchi depth and the other, there's a combination of variables which we use to check for the salinity level of water.
So,
But we usually use some field data from to check the salinity, the salt level, and then create a model using these variables. And so that is an indirect way of using remotely sensed data for to derive that.
Okay. And I have another question. Can I ask, or are there, Elga?
Yes, maybe a quick question, and then we move to the next.
As same thing in terms of temperature, which of these data sets would be ideal for us to kind of see if there's been an increase in temperature along the coastline and the estuaries?
If it is along the coastlines, I would really suggest to use Copernicus land surface temperature data, which also covers some of the inland water areas. The sea is masked out, of course, but there are two kind of products. One is land surface temperature. The second one is sea surface temperature. Sea surface temperature data is also available from Copernicus and also from NASA. So you can check USGS Earth Explorer. There you will find these surface temperature data sets. So
Okay.
MODIS was
Thank you
used
so
quite
much.
extensively. Was used quite extensively for land surface temperature, but for the last 2 years, there are some issues with the data. But for historical data set, it would be really good.
Okay. Thank you so much. Thank you, Elga.
Thank you. Then I think the next one was Violet.
Yes, hello. Yeah,
Hi,
so
Violet.
hi, how are you? Yeah,
I'm
my
good,
question,
Violet.
yeah, thank you. My question is with regards to, you talk about that you can use remote sensing to get volumes in lakes. I wanted to ask what we are looking for in our case study. It's the Athi River case study in Kenya.
Mhm.
We're looking to get volumes of water in wetlands. And just two examples. One of the examples is a wetland that it's a quaking bog. So it's covered by a layer of vegetation. But it is, and there's been an over abstraction of water, of course, for irrigation. It was messed up by a major road. And we'd like to know over the years, what kind of volume of water has it been holding? And you can use the technical terms because we have the technical experts within our team, which they'll be able, I may not be able to follow, but they'll be able, Solomon and Nirmala and also Claire, they're also part of the team. So just how would we know? Because we want to sit the farmers together so that
Yeah.
we can ask them, how are we are over abstracting from these wetlands such that the river that flows out of these wetland is drying up during the dry season, so it's affecting the people
Yeah,
downstream.
yeah,
Yeah,
yeah.
that's my question.
Water volume is, I didn't, I'm not sure if I mentioned water volume. Water volume is difficult, Violet. So water volume can be derived when we have both levels and water extent of a lake. Okay, and wetland will add more complexity because if we can get to the exact extent. So you have to check two databases. One is the Dahiti database. I think there is one more database on water levels. If that wetland has observation from this altimeter water levels, then there is an indirect way of connecting the water level versus the extent to come up with the volume. That is the only way. So there is an indirect way. There is no direct measurement of water volume. So it depends on whether we have water levels, either from field or from the satellite data which I showed, and the extent of the water body. And yeah, I cannot comment further because I haven't seen this wetland. But you are in good hands. So yeah.
Okay, thanks.
Thank you. I think in view of time, maybe I may ask the others with interesting questions, so either post them in the chat for Sajid to see, or to ask them at the end of the presentation of Belfrit. So at least we can cover that part as well, and then we can have a final session if we have extra time to then discuss additional points. So Belfrit, I think you are here. Are you ready to show your presentation to start?
Yeah, I'm ready. I'm very sorry. I was confused about the time because I think you
We
have
have
time
time
change,
change. Yes,
and
yes, no problem.
very sorry. But I'm here now, so I will share the screen. Can you see my screen?
Yes,
Okay, I put it in presentation mode. Does it work?
yes.
Okay. Okay. So good morning, everyone. I'm very happy to be here to share some idea and some result of some research we have done. And this research was part of one research financed by European Space Agency. And it was conducted with a team that you can see on the screen. And also we have some people from the University of Abu Mekalavi in Benin, and we have also some people from IIT Delft, and Sajid also was part of this work. So the idea was to develop a West African monitoring system. So say it like that, it's look very big, but it's a long process to have a monitoring system, and this work is only the very first step on that. So when you go to West Africa, mainly you see all those coastal lakes, you have many of them, and you can see them from Senegal up to Nigeria. They are but most of the time based on area with a lot of people and a lot of activities. And those lakes have some problem because since they are located in this such environment, they are having an increasing pressure coming from all the pollutant that people drop in the environment and drop in the water. So they are having some problem of eutrophication, and as the response of that, you have all those problem of water ascent invasion. But what is also so particular in some of these lakes is that people, they have observed the nature, and they realize that where you have mangrove, you have a lot of fish. And for that reason, they try to reproduce the environment. They use woods, dry woods, to create a kind of environment that is called akaja, and that help them to have some kind of fishery and more fish in the lake. So all those pressure on all those West African lake bring a enormous challenge. And the challenge for monitoring those systems, most of the challenge are due to lack of data. But also, when you have lack of data, you decided to have a data monitoring program, or you decided to have a data collection program. The challenge is the cost, because you need to send people on the field, you need to pay for all those costs, and it's quite expensive. And sometimes also, even when you have the fund to do that, some part of the system you cannot access them because there is a lot of challenge about how to go there and all those things. So now policymakers, they need to have new measurement, they need to have new ideas, new tools to help them to monitor those systems and to help them also to know what is going on there to propose a better management solutions. So that's what is the context of this study. And the idea was to use Earth observation data to develop open source online monitoring system. And we will monitor things like water quality, water ascent, and Akaja. So for the case study, we started with Benin because it is easier for us. It's the place where we live. And in Benin, we have studied two coastal lakes. So you can see it on the upper left on your screen, the location of those two lakes. But in this presentation, I will present only one, the result of only one, because it is a lot of results. So to, to, to stay in the time, I will present only one. And that one is what we call Lake Nokwe. Sorry, I did not put it on the slide, but I will add it later. So this the particularity of this lake is that it has two periods. We have one period where we have a lot of water that we call high water period. And we have another water period, which is low water period, obviously. But high water and low water are very different period because from one period to another one, the water quality of the lake change drastically because you have some salinity inputs when you have low water. So the lake is connected to the Atlantic Ocean. You can see it here. And when you have low water, all the saline water from the Atlantic Ocean go to the lake. But when you have high water, we have those big rivers coming from the north that bring a lot of water from this big catchment, which is most half of the country. So all the water become very fresh for those period of high water. In that lake, that is, you can see, we put here some satellite images. You can see that there are some formal geometries. You can see that there are some line on the lake. We will see it better on the images later, but those lines, they are the boundaries of Akaja, and you can see on an image here how they look like on the ground. And you also have this water that is have invasion of water ascent anytime there is fresh water in the system. There is a high invasion of water ascent. So that is how the study area is. So the idea of the study area is to build, the idea of the study was to build a monitoring system that will monitor water ascent, that will monitor Akaja that I described, and that you also monitor some parameter of water quality, and we choose chlorophyll A. So the first step is a classic step for research, is a method, classic method. We have literature, fieldwork, data analysis, and at the end, we try to develop some algorithm to detect based on satellite data, Akaja, and water assets. So from the literature, this is a very interesting because in the literature, there is a lot of work already that has been done on how to detect chlorophyll A. So we go through all those literature, we go through all these models that algorithm that have been proposed, and we look at what are the bound required, what are the result people get from the previous study, and what are the range of data to which that result can be applied. So that helps us to understand what is can be done for chlorophyll A detection. For water ascent, it's more different because now we have to do kind of detection based on different type of satellite images. So in this study, we try a lot of things, but what I will present here, it's what has been done with the only Sentinel-1 images, because we try detection with Sentinel-2 images, we try detection with Landsat images, but also we use some SAR data to try detection also. So what I will present here is only based on those data. And what is interesting to know about water ascent, what is interesting to know about Akaja, the picture, the first picture in the left here is how Akaja look like, what Akaja look like. This is an aerial photography. We take it from the plane, and you can see that it is almost some regular shape in which people put a lot of woods. So they were trying to reproduce a kind of ecosystem that can be favorable for fish to stay there. So an area where fish will feel comfortable, we have food and we go there. On the ground, that's how it's look like. But the problem is also when we go to high water period and we have fresh water and we have invasion of water ascents, you can see that all the gap between the Akajas, they are filled with water hyacinth. And you can see from satellite images that those green bands that you can see inside the squares, inside the regular shape, they are water hyacinth that's stuck in the Akaja. And on the ground, that is how it looks like. So here is very the beginning. So we try to develop an algorithm that take this in consideration. I will not go through the algorithm process because we can have more detail about that in one publication that we are trying to submit. But what is good to know about is we have two options in the algorithm. We have what we call bus plot analysis on the Sentinel-1 SAR data, and we have the O2 classification, which is the kind of automatic classification that use the Sentinel-1 band to give the best classification of an object we want to detect. So we try to compare what we call bus plot analysis, which is a manual analysis that look at all the data and it is very customized, and the OS2 analysis classification, which is more automatic, and we try to see that. So we also were having, since I explained that we have Akaja, we have water hyacinth, we were trying to define the classes, and the hypothesis that we have done here is that we have three classes we can detect. We can detect easily Akaja when we have low water, when salinity is there and there is no water hyacinth. But when we have water hyacinth, we can distinct, we can detect water hyacinth, or we can detect Akaja and water hyacinth because we feel like the mixing of water hyacinth and Akaja could be a challenge in classification. So that's what's the algorithm. So now for the data, we have some historical data for the chlorophyll A. What we have done for the study, which was 2020, 2022, 2023, we try to align our fieldwork to the date where the satellite data passed through. So we try to align that. And for the historical data, we try to choose what is the closest dates of the fieldwork data, and that at that date that we have images. So we try to do that. And that's what you can see for chlorophyll A. For chlorophyll A, I did not talk about the algorithm. The algorithm we use different band, and those band was taken from Sentinel-2. So for the Akaja and water hyacinth approach data collection, for the chlorophyll A, it is easier. We have all those 19 points and we follow them each month. We go on the ground, we take chlorophyll A measurement from the ground, and we now take satellite images. We try to see if there is a relation between those two, and we try to do a kind of linear correlation based on the model that was in the table I showed you previously. So that what has been done for chlorophyll A. For Akaja, we tried two approaches for data collection. The first one, we're trying to think that the population could help for the data collection. So what we did at the first step, we give them some training about taking information on the ground. So we give them information, take the pictures, we give them training like they can use their phone, take the picture anytime they see Akaja, and try to put the location on the map, on the picture, because when you take a picture, you can have the coordinate on the picture. So we give them some training to send us data, real data, when each time they go on the lake. So we did that with fishermen, but there was two main limits of this approach. The first limit is, you can see on the graph that there is not a representative coverage of the lake, because it's when they go out to do the activities, they take the pictures, and they take the pictures based on the place where they do more activities. And that is normal, because in the lake, we have Akaja everywhere, but the Akaja, they are still like fishery park, and they are like kind of private, even though it is not private, but people see it like private property. So the other people who use the lake for fishing, they are mainly concentrated in the rivers and in this part of the north, in the north. So there is this problem of representativity when you use this approach. The other limit is, people, when they want to take picture, they stay far from the objects. So they don't go inside the Akaja to take pictures, because it is a private, but also it is a lot of wood, it is difficult. And they cannot go in the middle of water hyacinth mats to take pictures also, because they will get stuck with the boat. So they stay at some distance, 5 meters, 2 meters, and that is not something that we can really measure when they are taking the picture. So it means that we have a coordinate of an object, but the object is not really at that point. It is like 10 meters away or 5 meters away. So it is a very difficult problem in detection. So since that approach was not really working fine, we now try to look at training data directly from Google Earth Map. So we use Google Earth Map for various years, and we try to detect on the map where is Akaja, where is water hyacinth, where is open water, and we try that, and we take 1,050, 1,500 points that we classify in three categories. Because when you want to detect something, you need to train the algorithm to detect that things, and to train the algorithm, you need to give ground data. So you need to give to the algorithm, here is water hyacinth, here is so that is what have been done here. And yeah, when we go on the field for the chlorophyll A, we can see the results. That is the result from the field work. And we can see from, I put here from 1919, the historical data in 2020, some data we collected. And you can see that there is a kind of cyclic variation in the chlorophyll A data. So we try to digitalize the map, to have the map of the distribution of the chlorophyll A. And from this data observation, there are kind of hypothesis that can be done, and we can think that to detect water hyacinth using Earth observation data, we might think to have two different type of model. We can have a model that can work for high water period when you have higher chlorophyll A and you have higher chlorophyll A concentration. And you may have another model that will work for low water period when you have lower concentration. But that will be a challenge to differentiate when I take a date. When I'm in high water and low water, it is really a challenge to differentiate that in the period of transition between high water and low water. And we're trying to think that salinity could be an indicator to have those differentiation. But anyway, that is the data observed. And this is the calibration. So and in the literature review, I show you a lot of algorithm, a lot of formula. We use the formula from Kero, and we use the one from Pereira. And we try now to calculate the salinity, the chlorophyll A, sorry, the chlorophyll A index based on those formula. And now we compare this chlorophyll A index on those formula. We compare it to the measurement we did on the ground, and we did some verification later. So we can see that for the two model, we have quite interesting linear regression showing that the model from Cairo and the model from Pereira has quite good approximation of the chlorophyll A data that is measured on the ground. So that is the first things. And now I will jump directly on Akaja and water hyacinth, and that is the data collected from the satellite. It is Sentinel-1 and Sentinel-2 data. They are based on polarization. So we have the VVVH and the polarization, and we try to see how those polarization vary during the years. And from 2019 to 2023, we can see that anytime we are in high water period, we can see that the value of the polarization change. So you can see here that it's increased anytime you have high water period. So that means that between those two periods, there is a difference in what can be seen in polarization from the images, from the detection of the object Akaja. And that is quite very long to explain, but what I wanted to show in this graph is that the model for also Akaja detection is having this kind of particularity, and the particularity is based on the presence of water hyacinth, but also in the fact that the water increased during high water periods. So it might be difficult to have a only one algorithm to detect Akaja and water hyacinth in both periods. It might be interesting to combine some algorithm for the two periods. But what is done here is to detect the range of interval of the polarization in which we have the better signal on the ground. And when we do that, So what you see
Belfrid,
here
I'm sorry
is,
to Belfrid, I'm sorry to
yeah,
interrupt. We only have a few minutes left, so if you can try to wrap
yeah,
up so there's time for
the
a
last
couple
part, the
questions.
last
Oh,
slide.
perfect. Thank you.
Yeah. So when we have here is some, we use some interval, we determine the interval for good polarization. And what I show here is the result is mainly the result of two interval. Is the result from one interval from 26. So it's the research, so that's why we have all those numbers with decimal numbers. But at the end, it's between 26 and 19 for the image in left, and 24 and 14 in the image of the right. The main things we have to understand here is the boundaries. So you can see it from the accuracy assessment. It's very difficult to know the real boundaries of Akaja, because it will depend of the range of interval that has been chosen. So we try now to use one data that was existing, where people, they go on the ground and they measure really Akaja. And we try now to compare what they have measured physically on the fields to what we have detected. So what we detect is in white, and what they measure in the field is in purples. So we can see that accuracy, and it shows that the model is quite good, but there are still some improvement that needs to be done. So here are the perspective, but I will not present them. And thank you for your attention.
Thank you so much. Very interesting work, and I think also very relevant for our project. So with this, I would like to open the floor for questions. In the group, I think there was already a hand up, but maybe from before. Or is it something for? So I see Stefan. You have a question for Wilfried, or is it? You have discussed that in the chat already with Sajid. Maybe Valentin?
Hey, good morning, everyone. And thank you for inviting me to this webinar. Okay, I'm going to ask the question for this presenter. For the first one, I will keep my question for the end. Thank you for the very nice presentation and the very nice job done. My own is not really a question, but I want to know your experience in working with satellite images. As we all know, in our area, mainly in coastal area, we have problem with cloud. Sometimes we may have satellite images, but they are very cloudy and then useless. How did you deal with this cloud to be able to have at least some good quality data to conduct your study? Thank you.
Yeah. So should I reply automatically? Yeah. Okay.
Yes, I was about to ask,
So
but if
yeah.
you want, yes, please.
Yeah, I will. I will. So for the cloud is a very big problem when you have in coastal area, and also when you are in that type of raining season where you have a lot of cloud, and sometimes it can just ruin your whole analysis. And that's why in detecting Akaja, we use the Sentinel-1, the SAR data that is that is not affected by cloud. So that is the first things we did. But when you want to use spectral data and you don't have any choice, there are some tools to help you to remove the cloud from your images. But the advice I would give also is sometimes we do it automatically. We say that, okay, all the image with more than 20% of cloud should be removed, but we don't really look at the image. And what I realized with my experience is sometimes you can have a lot of clouds, but your study of your place of interest it does not have cloud cover. So maybe sometimes you need to clip your study area very well before you start looking for clouds. But also all those images that were having a lot of cloud that you just want to reject because they have more than 20% or all those percentage of cloud, I will advise sometimes to look at them, because sometimes when for the lake, for example, I realize that sometimes for some images, it is only the western part of the lake that is cloudy. So there are still work that can be done in the eastern part and so on. So that's what I can say.
Okay. Thank you. Thank you very much for your experience. Thank you.
Thank you. More questions? I don't see hands raised.
So there is one question from the chat saying that is the measurement from nitrates? No, it's the measurement that shows in the graph. They are from chlorophyll A. They are from chlorophyll A. And all this here is about detecting chlorophyll A. So it's the measurement of chlorophyll A that was in the graphs.
Yeah, I was just
I
trying
have
to
a
answer.
oh, go
Sorry,
ahead.
I was just trying to answer because I read that again. It's nitrate and phosphate and total nitrogen, total phosphate. I think, yeah, the point is we have field samples. Usually, lake parameters are all computed using regression models, other than the common parameters like the chlorophyll, the turbidity, the organic matter, dissolved organic matter. So these are the three parameters which we have globally accepted models and ready to use products available in my exploration. Oh, and the products also give something called water leaving reflectance, because that is also important, because that is different from the raw satellite data, because it's been gone through. Those data sets are pre-processed with a step called atmospheric correction, which is suitable for water surface, areas. So those water leaving reflectances is the only option we have when we want to model any other quality parameters. But then we need field samples, which is, corresponding to that particular parameter which we want to model. So the questions related to how many points we want and all, even if it is, I mean, I would say for a lake, even if it is one sampling point with total nitrogen, total phosphorus measured, I would just go for and have a look into the model. But because at least for that point and that adjoint zone, um, that regression model should work. So I don't have a clear answer on how many sampling points. It depends on the lake size and other things, but this is how it usually works. So nitrate and phosphate, TN and TP, I don't think we can relate. We need a corresponding variable.
I see a linked question a bit in the chat from Charles Abebe for Belfrid, because of course, in theory, it's difficult to choose. And I guess the question is in practice, how you chose the in situ areas.
Accessibility,
Belfrid.
to be honest. Oh, it was for Belfrid, sorry.
I think it was for Belfrid, but yes, because for the specific case study like, I know you were
Can
also
you,
involved, Sajid.
I did not get it, please. Can you please repeat?
You can check the question in the chat if you want. Is from Charles.
Okay.
What criteria did you use to select the sites for in situ data in your research?
Oh, okay. So this lake I have been working on Lake Nokwe for like 10 years now. And with time, I really understand what are the different part of the lake. So the main criteria is to have some representative uh, sampling for all the characteristic of the lake, because there are a lot of activity in that lake, and from one area to another area inside the same lake, there can be a big change in water quality data. So I base the choice of data collection points to have a kind of representative data collection of what is happening on the lake. And this is done through the analysis of a long years of data collection. So that's how the point was chosen. So, but in that case, you don't have a lot of data collection. There are various types of strategy to choose the sampling point. You can have the regular meshes. You can decide to divide your lake in regular parts, and in each part you take some sampling points. Or you can also look at all the relation of the lake with other ecosystem. If there is a river, if there is some urban urban sewage or urban rainwater system. You can choose based on the activities around the lake. You can choose also your sampling point based on those activities. I hope the answer is clear.
Yes, thank you. Do we have more questions? I don't see anyone waiting. So if not, I think it's 12:06. We are almost on time. I wanted to thank you all for joining, so especially the speakers, but also all the group. And I would like to also invite you and remind you of the next session that will be in 2 weeks. Sorry, I
No,
don't
we're
have open
skipping
the...
in 2 weeks because there's this WDPP symposium, so it will be in 1 month.
In 1
So
month
those
time.
who want
Okay.
to join the symposium don't have too many things in their week.
Thank you very much. I hope to see you in 2 weeks for the WDPP symposium or in 1 month for our series of continuation of our series of webinars.